record. Started at 3:02. Okay. All right, and then let me switch over my share screen here to my phone. Let's connect this up. All right, looks like we got a few new faces from the before the break here. But to pick up where we had left off, just to let you guys know who might not have been here at the end of the last session, I promised Anthony here we would do number 18 here together from chapter 30. So that's where I'm going to go ahead and start, and then encourage any of you guys who might have another question to throw that into the chat. We're in some harder material. We've got a lot of questions. So if you have a question on one that I done in the earlier ones, I'll gladly do it again, but only if there's not other questions. Otherwise, I'm going to direct you to the recordings that we did earlier. So, for example, right before the break, I got a question for 36 and 37. And if those questions come back, I'll gladly do them. But at the same time, somebody told them in the chat that I had done them in section 1, and they could see it on the video. So they kind of popped out. So that might answer those ones here. But anyways, I've got these listed. But the one I have not done for any of the sessions here is number 18. So let me try number 18 and say a lot of the same things that I said before. There's just some angles and 3D visualizations and the two right-hand rules that can get really confusing here. And so keep working on these because they just need time to digest. And so hopefully you've been working on them this week, because it really takes 2 weeks for this chapter to sink in. And so you can have this week and then next week, and the test is right after that on the Tuesday. All right, so with that in mind, I'll flip back over here. Let me scan the assignment for number 18. 18 says, two long parallel conductors are separated by 10 centimeters, carry currents in the same direction. So maybe in my picture here, I'll draw wire number 1, so I'll call it current number 1, and I'll just draw it going, looks like from my right to the left, and then maybe another current here, current number 2, same direction. The two long parallel, okay, conductors, separated by 10 centimeters. So I'll put a little 10 centimeters here. The first wire carries a current of 5 amps, okay, so I'll put a 5 amps. And the second one carries a current of 8 amps, okay. What is the magnitude of the magnetic field created by number 1 at the location of number 2? All right. Well, there's 2 ways I want to answer this. I will do the short way first, and then maybe this will be helpful for anybody who's wasn't around earlier here. But the Ampere's law method, if I can draw in blue here an Amperean loop. Oh, and shoot, now I'm confused which one was 1 and 2. They said, what is the magnitude of the magnetic field created by number 1 at the location of number 2? Okay, so I'm going to draw an Amperean loop. And your author has been doing it in blue, so I'll draw it in blue. that number one goes right through. And so in my mind, let me point out that I'm ignoring current number two for just a second, okay? And I can just ask this question: what is the magnetic field along this Amperean loop? And this is where Ampere's law can be quite useful. Ampere's law is identical to Gauss's law, or maybe identical is not the right word, but it's the same kind of idea where you add up the field. Now, in Gauss's law, just to remind you, we were adding up the electric field on a surface. And then that was equal to the charge inside of that surface, so the charge inside of a three-dimensional object. Ampere's law is one dimension down, but it's the same idea. You add up the magnetic field on a loop, okay, on a line, not on a surface. And it is equal to then the, and related to, there's this epsilon naught instead of a mu naught, but, I mean, a mu naught instead of an epsilon naught. But there is this current that would go through the surface that is enclosed by this Amperean loop. And that's what I'm going to do. So I'm going to apply Ampere's law to just a long straight wire. So again, for the moment, I'm going to just look at current number one, because that's the question. What is the magnetic field created by number one at the location of number two? So I drew an Amperean loop that had this radius of the 10 centimeters. And like we did with Gauss's law, the first part is to take the dot product. And the Amperean loop that is helpful is the one that will allow us to do a couple of things here, just like the Gaussian surface that was helpful. So the one that is helpful would be the one that you could argue that even though you don't know what the magnetic field is, you know it's a constant everywhere that you're doing that integral. And so you could pull it out in front of the integral, because it's impossible to do an integral with a function that you don't know what it is. So you've got to justify pulling it out in front, which can only be done with constants. So the argument goes along these lines, just like it did for a Gaussian surface. This Amperean loop, if I maybe put myself somewhere on the loop, maybe here, maybe here, maybe here, maybe here, maybe here, maybe here, doesn't really matter, any of those 6 places, I would say as I stand on this loop and I look at the current that is making the magnetic field, it all looks the same. I'm looking back at a distance of 10 centimeters. So therefore, whatever field is created by this current of 5 amps, it must be the same everywhere along that Amperean loop, because even though I don't know what the equation is, I do know the physics. The magnetic field comes from the current. And so that was kind of our argument about the electric field, and I'm going to do that same argument here for the magnetic field. Now, the other very helpful thing about the Amperean loop, just like it was for the Gaussian surface, is looking at symmetries and looking at why the field was created in the first place. We should be able to say something about the direction of the field, even though if we really don't know what the equation is. And of course, if you recall, when we did Gauss's law, we would have something like this. We would have like this spherically charged ball, and then we would draw a line of symmetry through it. And we would say, okay, if you kind of flipped it, that's maybe I should have drawn this on something I could flip real easy on the camera. I'm going to do a little post-it note here. Okay, so I'll kind of redraw. If I take charged ball, uniformly charged, the same throughout, and draw a vertical line, let's say, through the middle of the ball. The argument is that if you were to flip it, what would you get? And this time I'll take advantage of the red ink bleeding through. And I would say when you flip it, you have the same charge distribution. So what that meant back here is that if there's some field at this point, and of course I'm kind of reviewing the electric field here, but if there's some electric field at that point, when you flip it, since you end up with the same charge distribution, the field should be in the same direction. So if you had an electric field that was kind of pointing like this, so before I flip it, if you said, well, I think the electric field is down and to the left. So when you flip it, it's now down and to the right. And that should bother you because you're like, well, wait a minute, how could this charge distribution make the field down and to the left be different than the same charge distribution, now making the field down and to the right? That makes no sense. And of course it makes no sense. And so that would tell me that you can't have the field that way. In fact, the extension of that argument is that the field could only then be along a line of symmetry. Because when you flip that, the field is still along that line of symmetry. So we know that if we ever have a line of symmetry, and in this case it's an electric field, the electric field created by those charges must be along a line of symmetry. So that was our big argument in chapter 24. So I hope you haven't forgotten that, because I'm going to do something similar but a little different, because these are not going to be lines of symmetry. They're going to be lines of anti-symmetry. Here's what I mean by that. Let me get another Post-it note and say this, that if I had a current that is flowing, and in my picture, I will draw it from my right to my left, and it's a really long wire, and I draw a vertical line through it, and then I flip it. What do I get? Well, when I flip it, I get the same amount of current, but going in the opposite direction. And so almost everything is the same. That is, I've got the same magnitude of the current. I got the same, I'll call it distribution of the current. But what I don't have is the same direction to the current. So here's what that would tell me. That would tell me then that whatever field is made from this line of current, when I flip it, that field should flip exactly 180 degrees. It'd be the opposite direction. It would be the same magnitude, because everything in terms of the magnitude of the current and the distribution of the current is the same, but it would be in the opposite direction. And so that's why we call it not a symmetry argument, but an anti-symmetry argument. The positioning is the same, but the directions are different. Okay, so now back to the original. So what direction would it? Would that create then a magnetic field that was down and to the left? Because when you flip it, you now get down and to the right. Well, that's not opposite. Certainly the left part now becoming a right part is opposite, but it's still down. So no, you can't have a field like that. And in fact, could we have the field along the direction of symmetry, like we did back with Gauss's law? No, because again, when you flip that, you get a field that is still the same direction. It didn't change directions. Okay, so with an anti-symmetry, we argue that you would not get a field along the lines of symmetry. That's what we argued for symmetries. So for symmetries, we argued that the field would have to be along the direction of the line of symmetry. So you flip it, it's still in the same direction, which is why we say it won't work in this case. When you flip something with an anti-symmetry, the field is still in the same direction. And that's not what we expect to happen from the physics. We expect that the field would be opposite. So what direction would it have to be? And the answer is then perpendicular to a line of symmetry. So that when you flipped it, you now got it in the other direction. So for magnetic field, we focus our attention more on an anti-symmetry than a symmetry. And that's what I have here. I have the argument that the magnetic field here must be then perpendicular to the current. Now, sadly, perpendicular could mean a lot of things here. It could be, in this picture, in the same direction, well, I'll put it this way, as current number 2. It could be opposite direction number 2. It could be tangential to the circle pointing out. It could be tangential pointing in, because this here would be a line. However, when we incorporate another line of anti-symmetry and you flip it, we could rule out the ones that were not in the plane of the Amperean loop. So therefore, that tells me that the only possible directions for the magnetic field that still would obey what the basic physics is saying, that is, it is coming from the current, and it has this anti-symmetry about it, then I know that the magnetic field must be tangential to the Amperean loop and pointing in the direction of the Amperean loop. And so this would tell me that this angle could be 0 or it could be 180 degrees. Now, cosine of 0 is 1 and cosine of 180 is -1. So it won't really matter which one I pick if my goal is just to find out what is the magnitude of the magnetic field. I'll just call that a 1, whether it's really a -1 or not. Now, I will say, though, even though the physics doesn't allow us a true definition of the direction, that's where our human definition comes from. So all we really know from the physics is that there would be these lines created by these magnetic fields that in the case of a wire would be a circle around the wire, or in case of a bar magnet, if I can review back to chapter 29, North Pole and South Pole, they would be these lines that would go from one pole to another. And it was us humans who decided that we're going to define in a direction by saying the lines start at North Poles and go towards South Poles. And then we invented this whole right-hand rule thing to try to help us get that straight. So what I'm trying to say here is this then would be my thumb points in this direction, and I would say then that since my fingers curl around in the direction, if I'm looking from the top here, would go in here and out here, and above the paper would go across the top, and below the paper, if I can pick up the paper, the field would go underneath. So that's just the definition of the direction. So the physics just tells us that the field's got to be pointing in a circle. It doesn't really tell us whether it's going to be a clockwise or a counterclockwise. But looking from this side, looking from the right-hand side, it would go around in a clockwise direction. So again, depending on which way I do my integral, so if I do my integral in a clockwise direction, the angle would be 0 degrees. But well, I guess it was good that I talked about direction, but I wanted just to run through Ampere's law to figure out the equation for the magnitude. And of course, to do that, I didn't really need to pay any attention to the plus or minus. But it's this one here that turns out to be an easy integral to do once I've done those two big steps about saying the symmetry argument or the anti-symmetry argument, because these would then tell me the field is a constant, I can pull it out, and this would tell me the angle is either 0 degrees or 180 degrees, depending on how we define it and which way you go on the loop. But the bottom line is you're just left with an integral of ds, and that means just integrate along the loop. ds is a little bit of a step along the loop. So if you add up all the steps along the loop, you're going to get the full circumference of it. So this is 2 pi r, where r is the radius of the ambient loop. And the other side of the equation, this is the easy one. This is the current that goes through the ambient loop. So in this case, if you make a loop that goes all the way around current number 1, then all of it, all 5 amps, goes through there. And so we end up with the equation for the magnetic field from a long wire that looks like this. And so I would encourage you to commit that to memory. That's kind of the basic, a long straight wire, technically an infinitely long straight wire. This is the magnetic field. And that's what I'm going to use for this problem. Now, in passing, I will mention that if the wire is not infinitely long, you have a number of those. This was the first equation derived in the Survey book that said you could calculate the magnetic field from a finite size wire. So if the current was here to here, and the way it was derived, the current was going from left to right, and the point P was up here, and the angle 1 was defined like this. So angle 1 was the angle of drawing the two lines from P to the current and then P to the beginning of the current. And then angle 2 was defined this way, of drawing two lines, one from P to the current perpendicular, and the other one is from P to the end of it. And stuff that swung out this way was considered positive, and stuff that swung out this way, which would be counterclockwise, was considered negative. So if you follow that derivation, you could actually do the magnetic field from a finite size wire. And so I probably shouldn't spend too much time there on this problem because this is not a finite size wire. So I'll just cross that out. But I know that a lot of you are still learning this, kind of struggling with this. And so your author has done both. In fact, he did the finite wire first, and then he took the limits of that, saying if this was an infinite wire, this would, theta 1 would go up to 90 degrees, and theta 2 would arc out to negative 90 degrees. So this would be a 1 minus a negative 1, which makes a 2. That 2 would cancel with that 4, and you would get this equation. So your author, I think, did a really good job, and hopefully I did too in the lecture, showing you that once you work out B-ups of art for the field from a finite size wire, you can just extend that to a special case of an infinitely long wire and get an infinitely long wire. You could also do Ampere's law for an infinitely long wire. Sadly, you cannot do Ampere's law for a finite size wire. So our arguments wouldn't, symmetry arguments wouldn't hold. But for an infinite, and I should say anti-symmetry arguments wouldn't hold. But our anti-symmetry arguments would hold for the infinitely long wire. And so that's why I did this. And so I've got the magnetic field from an infinitely long wire, whether you want to get it from a finite wire extended out with B-ups of art, or if you want to do it with Ampere's law. I think it's a little easier with Ampere's law, so I thought I'd start this problem that way. I would even say, too, if you're doing the homework, you wouldn't want to go here and derive this equation. I was doing that for your advantage. So commit this to memory, or since the test is open book, know where it is in your book. And know if you ever have a long straight wire, this is how you get the magnetic field. So if you know that, it actually makes this first question of problem 18 really easy, because it asks for the magnitude and the direction. So in terms of the magnitude, it would just be mu naught times I over 2 pi r. So I would just put in my numbers. U naught is 4 pi times 10 to the negative 7. The current, now I guess we got to be a little careful saying the current is from which wire. So they're saying here, what is the magnetic field at wire 2 created from number 1? And so it's current number 1 that we would want right here. It's the 5 amps. And in fact, let me just switch back, make sure I'm reading that right. What is the magnitude of the magnetic field created by number 1 at the location of number 2? Yep. So created by number 1. So 5 amps, the one that's creating the magnetic field. So the magnetic field at number 2 is created by number 1. Right, so that's 5 amps. Then I can divide that by 2 pi, and they would be asking for the magnetic field at wire number 2, which is 10 centimeters away, although let me put it in as meters. In fact, I should be a little careful here with the units. This is a meter. This was an amp, and this permeability of free space had units of Tesla times a meter over an amp. So that the amps cancel off and the meters cancel off, and so we're going to be left with a field just in Tesla. So I hope I didn't bore you too much and take too long going through Ampere's law. Like I said, for this problem, I really think the author was just saying, start with this equation and just plug and chug here. So I'll save myself some keystrokes on my calculator by canceling a 4 pi with the 2 pi, leaving me with a 2. So this would be 2 times 10 to the negative 7 multiplied by 5, and then divide by, and I don't have to worry about the 2 pi anymore, just the 0.1. And so this would be 1 times 10 to the negative 5 Tesla, or maybe I could write it as 10 times 10 to the minus 6 Tesla, which is 10 micro Teslas. So that would be the magnitude. And they didn't even ask for direction. I think that's going to be necessary in a moment here. But I'm going to switch over to the answer, and they say 1 times 10 to the minus 5. Oh, they even say coming out of the page. I don't know if we have to answer that out of the page. It didn't seem like they were asking it. It literally said, what is the magnitude? But as long as they're answering it, and maybe if it will be helpful, I'll do the same thing. Here's this little trick. I call it right-hand rule number 2, because it's not to be confused with the first right-hand rule you learned. In fact, let me point out, I was doing this in one of the sessions, I think it was the first one, that the very first cross product you learned was in Physics 121, where you took R cross F. And then the second one you did was R cross linear momentum, which gave you angular momentum. And so last semester, or maybe 2 semesters ago in Physics 121, you were doing this right-hand rule for cross products. Now, we saw some cross products already this semester. We saw magnetic moment cross magnetic field is equal to the torque. We also just saw in this chapter some B-ups of art that you could calculate the little bit of magnetic field by taking a cross product between the little direction of the current, and that's the magnitude of the current, and a vector, a unit vector pointing to where you want to know the magnetic field, but there's another cross product. So I would say at this point in your education, you have done 4 cross products, and they all involve, putting your fingers in the direction of the first one listed and closing towards the second, and then your thumb gives you the direction of that cross product. But we have another, which I like to call a second right-hand rule, that gives you the connection between the current and the magnetic field. And that one's a little different, but because we call it the right-hand rule, it's a recipe to confuse and think we're doing the same thing as a cross product, and I am not. So that's why I want to call it right-hand rule number 2. Right-hand rule number 2 says do this. Take your right hand and hold it with a thumbs up. Your fingers are already curled. Do not do any kind of closing thing. This is not a cross product. This one's totally different. You don't move anything in your hand. You just hold your right hand with a thumbs up. And if you have a straight wire, since your thumb is straight, that becomes the current and your fingers become the field. If you have a curved wire, then your fingers are the current, and your thumb is the field. So notice I can't say that my thumb is always the current or my thumb is always the field. They reverse roles. So you have to look at the problem you're doing. If you have straight wires, use your thumb for the current. If you have curved wires, use your fingers for the current. And the other one will give you the field. That's how you remember it. So in our problem, I've got straight wires. So that means if I do right-hand rule number 2, I would then be using my thumb as the current. My thumb is straight, the wires are straight. So put your thumb in the direction of the current. Okay, so there it is. My thumb is in the direction of the current. So maybe I'll hold it this way so you can see my fingers better. But see how my fingers curl around? This would tell me that my field would curve around the wire. That is, they would come out of the paper below this wire number 1, curve over the top, and go into the paper. So if I said into the paper, above it, I would put a little X, and coming out, I would put a little dot. So this would be coming out of the paper, which, let me swing back to the answer. And what does he have? Out of the paper. Well, he's also got them listed a little different than me too. See, that's going to be kind of the dilemma. But actually, I like the solution. He shows somebody with a little right hand there. That's kind of nice. But he did draw his currents going from left to right, and then he drew number 2 above number 1. So he's got a little drawing different than me. So since the author didn't give a drawing, I suspect that's why the author just said, hey, don't really tell me the direction, because that's kind of depending on how you label your currents and what direction they are. So just give me the magnitude. So anyways, I probably shouldn't have messed with direction, but hopefully that was helpful because it only asked for the magnitude. All right, so I've got the magnitude of the field. But I think I'm going to need direction as I move on, because look at part B of 18. Part B says, what is the force per unit length exerted by number 1 on number 2? So this is going to take me back to chapter 29, because in 29 we learned this little formula. This was the formula for figuring out not only the magnitude but also the direction, because it's a cross product, the force on a wire of length L carrying a current of I in a magnetic field of B. And so this question B is asking, what is the force on number 2? So coming back to this equation, I would say then this must be current number 2. What is current number 2? This would be the vector of number 2, the length of that wire. And then this would be the magnetic field where number 2 is. That means it's the magnetic field that was created by number 1 at the location of number 2. And that's what we just did here in part A and got that number. And we also got it coming out, or the k-hat direction, if you will. So let me start by saying, let's just calculate the magnitude of the force. So this would be the magnitude of current 2 times the magnitude of the length of the wire of number 2 times the magnitude of the field created by number 1 at the location of number 2. That's where the current is. That's the number we did in A. And then the sine of the angle between them. Well, that's where our picture has to come back into play, where we said the magnetic field at number 2 coming from number 1, here's the right-hand rule, is coming out. So it's going kind of in an upward direction. Like if I use my pen here, it's coming up. And the current is along the paper, so that's 90 degrees. And so the angle between the current and the field is 90 degrees. So the current here is 8 amps. The length of the wire, I'm not really told, but that's okay. I don't need it. You'll see that. The field is what we just did as 10 times 10 to the minus 6 Teslas. And again, coming out. And then sine of 90 degrees is 1. And so I will move the L to the other side of the equation. And now you begin to see why the question didn't ask for the force, it asked for the force per length. So we don't know the total force because we don't know the total length, but we do know the force per length. So treating that as one quantity, force per length, I then have 8 amps. Oops, 8, when I put 80, 8 amps, and a field of 10 to, well, 10 times 10 to the minus 6. And if you remember, a Tesla is a force of 1 Newton per 1 charge flowing with a meter per second. And then that coulomb per second right there is an amp. And so we're going to be left with the appropriate units of newtons per meter. What is the force per meter on this wire? So what is the magnetic force? Okay. So now I just have to multiply that. And of course, 8 times 10 is 80. And 8 times, and then, okay, that's 80. And then times 10 to the minus 6, I'm just going to write that as micro. So the force per unit length is 80 micronewtons per meter. Now, that's the magnitude. Let me also then come back here and get direction, okay? And so the direction, we need a cross product. Oh, I should have put that up here. The cross product. Yeah, we had some other cross products we've already seen. We've V cross B is another one. And then this one here, L cross B. I is a force. Yeah, 1, 2, 3. So we've seen 4 cross products this semester.
I think your camera froze.
Oh, bummer. Let me reconnect. I wonder if I should have hit stop sharing before I reshared. Oh, seems to be okay. All right. So what I was saying when it froze was that it just dawned on me when I got here that we had these other 2 cross products in chapter 29, and then we had this one in 29, and now we have this one in 30. And then group that with the 2 we saw in Physics 121. So we find a number of cross products. And like I said, that's what I call right-hand rule number 1. And that's how I want to get the direction. So now that I just calculated what the magnitude of the force is, I want to go back and use right-hand rule number 1 and use the cross product to find the direction. And so it says the first vector is L. That's the direction of the current. All right, so coming back here, L is going from my right to my left. So I put my fingers in that direction. And now I have to adjust my palm so that I can close towards the magnetic field. So for you guys, that would be up, because we said that the magnetic field from number 1 comes up. That's how we got from the second right-hand one. So don't forget how we got that one. But that's not what I'm doing now. I'm not doing the second right-hand one. I'm doing the first one. I'm trying to do a cross product between the current and the field. So the field is up from wire number 1 at the presence of wire number 2. So that's why I put my fingers here and cross that, and I'd get my thumb pointing upward. And so that is saying that the force on number 2 is up towards wire number 1. And so I'll just say toward number 1. So in other words, they're attracted together. Although I guess I still have to talk about what is the force on number 1. But this is the force on number 2. So number 2 is being pulled in towards number 1. And I suppose I should just double check with the solution. Yep, they say 8 times 10 to the minus 5 and towards the first wire. Okay. Now I'd say there's 2 ways then to do part C. The easiest way is almost too simple, and I'm not going to teach you anything new, so I'll mention it, but then go to the harder one here. But part C then says, what is the magnitude of the magnetic field created by number 2 at the location of 1? Oh, that's not the one I was thinking of. I was thinking of D. What is the force per unit length exerted by number 2 on number 1? And for D, I'll just put D down here, we could really invoke Newton's third law, because we just calculated the force on number 2 from number 1. So the force on number 1 from number 2, would it be exactly equal but opposite? And so in my picture, I would have to say then that number 1 has the same number, which is that 80 micronewtons, but in the opposite direction. So it's 1 puts a force on 2. That means 2 puts an equal and opposite force on 1. That was Newton's third law. So that's why I say that's not very enlightening. That is just redoing physics 121. But it's nice to know that we could use it. But I'll just stick to the magnetism. And so let's go to what C said. C said, find the magnitude of the magnetic field created from wire number 2 at the location of number 1. Well, since wire number 2 is also a long wire, and let me not go through Ampere's law again, we can just use that result. So I will put in my 4 pi times 10 to the negative 7 for mu naught. Now the current for number 2 wire is 8 amps. And we're trying to find the magnetic field at the location of wire number 1. And so that is still 0.1 meters away. So I want to say then that this is essentially the same calculation I did in A, except in A, we were talking about the field from wire 1, so we used 5 amps. Now we're talking about the field from wire 2, so this will be a stronger field and a bigger number. But as I cross out the 4 pi and make it a 2, because of the 2 pi, it'll save me a couple of keystrokes on my calculator. So this is 2 times 10 to the minus 7, then times an 8, then divided by a 0.1. And so this would be 1.6 times 10 to the negative 5 Tesla. And then I could say I'm done, but I'm going to redo D, not using Newton's third law, but let's just go back to our new stuff we're learning, our magnetism. And so let me go back to chapter 29. This is what we said would be the force on a wire in a magnetic field. So in this case, we're trying to find the force on number 1. So here I'd put current number 1 and the length of the wire of number 1 and the magnetic field that is created from number 2 and then the angle between them. Now I'll put 90 degrees, but let me justify the 90 degrees again. Let's come over here and look at it. If we try to find the direction of the magnetic field at wire number 1 from number 2, we need to use the right-hand rule again. Now this is right-hand rule number 2. So number 2, it's none of this closing of the fingers. Number 2 is just hold your right hand in a thumbs up position and look at the currents you have. If you have straight currents, use your thumb for the current. If you have looping or curved currents, use your fingers. Now I have straight ones, so I'm going to use my thumb for the current. So with my thumb pointing in the direction of current number 2 and looking at my fingers would say the field would come up out of the paper here, arc over the top of wire number 2, and go down in to the paper here. So I would say the little x, that the direction of the magnetic field from number 2, but at the location of number 1, is down into the paper. Now, of course, remember the current is going from right to left. So the angle between straight down, so if I use this green pin as straight down, and I use this blue pin as straight across from right to left, I think I said it wrong there before, then that would be 90 degrees. And that's where I'm getting this 90 degrees in my calculation. So then I can just put in current number 1, there's the 5 amps. Per length, I'll just move it to the other side. So the L, and that's what we're asked to, the force per unit length. The magnetic field is what we got over there, 1.6 times 10 to the negative 5 Tesla. And if you get out your calculator here, 5 times 1 is 5, and then 5 times 6 is a 30, so 5 and 8, that would make 8. So that would be 8.0 times 10 to the minus 5, and a Tesla, again, is a Newton per coulomb, meter per second, so that's coulomb per second is an amp, and we're left with newtons per meter, or as I wrote it, 80 micronewtons per meter. And so that does match Newton's third law. So like I said, this would be a much shorter problem if I just kind of plugged and chugged into it. And that's, I think, was the intent of your author. So feel free to do that. I'm just taking this a little longer because I think it helps with your understanding. But if this was a test problem, definitely just, hey, you already know this, boom, get the magnetic field. And that's the answer for both A and C. And then the answer for B and D, well, once you do B, you don't have to do D again because of Newton's third law. But I'm glad I did. And I should also do direction. So to finish this problem, let me come back here using this equation again and using right-hand rule number 1, I got to do a cross product. Okay, so I need to put my fingers in the direction of the current of wire number 1. So here's wire number 1. So I'm putting my fingers in the direction of wire number 1. And I have to adjust my palm until I can close my fingers towards the field. And as we said, the field coming from number 2 is down. So I would have to adjust my right hand like this. So I can close my fingers down. And so my thumb is pointing down, and sure enough, there it is, the force is down. It's towards number 2. And so again, these two forces are equal in magnitude, opposite in direction. And so I could put here down, or maybe better, toward wire number 2. And where did I get answer B? Yeah, see, answer B right here was the 80 micronewtons per meter toward wire number 1. So that's, hopefully didn't take extra long time, but that was the, I guess my goal here is to kind of show you that if I go through all the bloody details, Ampere's law, I get the equation for the field, but you could have just started there. And then I could also do the cross products. And so notice I was using both right-hand rules, one to get the direction of the field and the other one to do the cross product. I can figure out that the magnitude of the force on, number 2 here, or on number 1 is the same as what we got on number 2. All right, good. Well, I hope that was helpful. Let's see. I get a question here from Gina. I have to go to work. Thanks again, Professor. For the video solution for number 18. Oh, it looks like she didn't quite see the end, but she will, I trust. And so she had to take off to work because she was asking that too, and so was, I think, Anthony there. All right, I don't see another one in the chat. Does anybody want to throw one verbally at me? If no one has a question, I have a question about formula.
Yeah, and then if he wants to go do that, and then if we could do 53 on number 30, that would be awesome. Okay.
53, it doesn't sound like I've done that one yet, so good. I'll gladly do 53, but go ahead, Daniel. If you have one on the formula, let me answer that one.
Yeah, so it's that, it's the formula for the finite wire where you have the sine 1 theta minus sine 2 theta.
Oh, yeah.
I found some of the solutions that they use the cosine version of that. When would it be okay to use the cosine version of that versus the sine version?
I am so glad you asked that, because so the first thing I'm going to say, and let me give me a second to make sure I don't mislead you. Let me go to my YouTube channel, because there was a good question I got last night. Shocked me a little bit. Problem number 14, okay?
Mm-hmm.
I worked out the video solutions. You probably haven't got a chance to go through it yet, okay? But in problem number 14, the author uses the cosine version. Oh, excuse me, before I say author. The author of the solution manual uses the cosine version. I decided to do the solution using the sine version, because that's the way it was taught in the lecture. I think it's a little better, but you'll hear me say this in the solutions there, and it took me like 45 minutes to explain it, that they both work. So I did it both ways. Now, I still want to answer your question. I don't want you to take this as I'm blowing off your question and telling you to go look at the solution, because you just need to hear it more than once, okay? So I want to tell you that I'm going to explain the difference here in a second, okay? I might even use it if you want me to, but somebody asked about 53, so we'll see what 53 is, and I might use it. But I used it both ways in problem number 14, and I know that it can lead to some confusion, and so that's why I wanted to do it both ways. And so, like I said, it made problem 14 too long. Like I'm looking at it now, it's 42 minutes and 36 seconds. But I think by me doing both methods, it will really help answer your question about when do I use which one? And the best answer I can give you is they're both valid. You just have to understand what they mean, okay?
Okay.
That's the most important thing. So I'm going to take a moment to explain both of them, but not necessarily do them, okay? So if you have a finite wire and the current runs from left to right, and you pick a point P above it, I worked out using B-ups of art in the lecture, and Surway also worked it out, that you come up with this equation. This is what I will call the sine version of the equation, okay? Now let's talk about the meaning of these. The easy two are the current and the A. I is just the current in that wire. It's okay. A is the perpendicular distance to the point P that you're trying to find the strength of the magnetic field that the current is making. Okay. The hard one is what is the angle theta 1 and what is the angle theta 2? And here's how theta 1 is defined. If you draw a line from point P perpendicular to the wire, that's one line, and you draw another line from point P to the beginning of the current, that is the definition of theta 1. The definition of theta 2 is kind of like number 1, except you're going to draw a line to the end of the current. So I'll say it again, theta 1 is this angle between a line from P to the wire, perpendicular, and P to the beginning of the wire. Where theta 2 is the angle from P perpendicular to the wire and P to the end of the wire, okay? So theta 1s and theta 2s are up here in P. Now there's also one little important subtlety, and you'll hear me say it about 7 times in that solution to number 14, that your author has chosen during the derivation to call theta 1 a positive number. That is, things swinging in a clockwise direction are positive, and things swinging in a counterclockwise are negative. And that's kind of the reverse of tradition. And you'll hear me say it in the lecture, there's kind of an advantage of getting away from the tradition, but you got to know that it's away from tradition. Otherwise, you might put in a positive and negative in the wrong way, okay? So use that to get the magnetic field from a finite wire. Now, there is another very common procedure to list the same thing, starting with a current of I and some point P, a perpendicular distance away of A. And that equation is what I'll call the cosine form. And what is very important is the definition of theta 1 and theta 2 are different. It doesn't matter which one you use, you will still calculate the same field. But here is how theta 1 is defined. Theta 1 is defined as this angle in here. The angle between the direction of the beginning of the current and a line that connects the beginning of the current to point P. And theta 2, this is the harder one, this is why some authors, and Surway is one of them, don't like the cosine form, because theta 2 then is defined as the line between the end of the current and point P and the continuation of the current. So this in here would be theta 2. So theta 2 is kind of outside of this little triangle that's formed.
Okay, I see.
So, yeah, so if you see that difference, to answer your question, either one is correct. It's just if you're going to use this form, you need to know that in the derivation, they are using their definitions of theta 1s and theta 2s this way. And so theta 1 is up near the point P and theta 2 is near the point P. And then this definition gives theta 1 as positive and theta 2 as negatives. But this definition, of course, does have a nice advantage in the sense that there is no negative angles. It just, at the beginning, and then the angle gets bigger. And if you kept going, the biggest it would ever get is 180 degrees. So you don't have to worry about positive or negative angles. They're always positive angles. So that's kind of the nice thing about this form. Maybe the bad thing about this form is the angles are not near the point P where you're trying to get the field. They're kind of away from it. And this one, number 2, is outside. So to me, they're about equal. I actually learned it this way. The book I learned it from, if you've ever done any scanning of the other books, it's Halliday and Resnick. So it's a great book. Of course, way back when I was taking this in the 80s, it was the most popular book, and then that kind of got surpassed in the 90s by the Survey book, maybe a little later, maybe the 2000s. So the Survey's now become the most popular book. But they're still both very common and very popular. I'm not sure if the old Halliday and Resnick switched to this form. I know the original Survey actually did it this way. And then somewhere probably about the year 2005, the Survey book switched to this one. So you'd have to go back to a lot of editions to see this form. But the reason I wanted to do this one is I got a question on 14 about the angles. They were confused. And I wanted to then not only straighten out the angles, but also straighten out this equation, because the individual who did the solution set actually used what you're talking about, the cosine form. Oh, I should have wrote down when I started talking about this. Bummer.
It was like 10 minutes ago.
About 10 minutes ago.
Yeah.
So if
Like
I said
355 or something.
I'll say 355. Why not? 355. It'll be in that area. I'll put approximate. Okay. But I wanted to take, and I hope not too much time, because I think the best way to answer your question, Daniel, is what I just did now, and then say, please go spend a long time looking at the video solution to number 14, and then pause it often and come back, because it really points out that, and I'll just say it one more time, both of these equations are valid. So you could learn either one. Just since Survey and I derived this one, this is what I would recommend. The only tricky part is to remember when the angle is positive and when the angle is negative. And this one, the tricky part is to realize you're using cosines instead of sines, and you got to use that outside angle. So both would work.
I actually just finished 14, and I tried it the cosine way.
Okay. Because that's how the solution manual did it.
Yeah. So I tried it that way just so I could check my answer, and yeah, it was really confusing because I was looking through the book and I only saw the sine version of that formula.
Okay.
So yeah, I'm definitely gonna go through that number 14 video very thoroughly.
Good. But also, to keep your brain straight, I would suggest just pick one and stick to that for learning and for doing the test. Don't worry about the two different options. That's just more clutter in your brain for now.
Yeah. Okay. Thank you.
Would you say that there's like an advantage to using one versus another?
They both have advantages and disadvantages. But I would say the best one, really, since I derived it this way, your author derived it that way, this is the one to go. It's kind of sad that the person doing the solutions used this form because they did not match the author, and that is really the only reason this question even, I think, came up, because there's I don't know how you guys would even have seen this equation unless you looked in another book, or if you looked at the solution, or you Googled it somewhere, because I think you would have, this would have been a little cleaner. Although it's good to be exposed that there are other options, that's true, but it would be a little cleaner if the author just had done this one and the person doing the solution actually used it.
Yeah, I
Actually,
noticed in a
I
few
noted
different
this in
solutions.
the lecture videos because I have it in my notes, the cosine one.
Oh, in the lecture video, it's a cosine?
Yeah, I'm pretty sure you derived the cosine one, and then you told us about the sine one is what the book did.
Oh, okay. So, okay, so that's my bad. I did both. Maybe I shouldn't have exposed you to both. I don't know. I to be honest, I don't know. I think it is better to know both, but not if it makes your brain cluttered and you can't do either. Yeah.
Well, that
Yeah.
answers that question. Thank you.
Oh, yeah, that's right. Okay, so now let me write a time down here, 4:08. Okay, and let me jump to number 53 and see what that one is. That one's kind of high in the numbers. I don't think anybody's asked that, or even if I've even looked at number 53, but problem chapter 30, number 53. Let me switch over here. And that, oh, that's not even on page 1. Let me go to page 2 of this, and 53, yes. Oh, the Helmholtz coils. Great invention. And in fact, the lab I need to make this week, we have a set of Helmholtz coils. Yeah, so I'm going to be talking a lot about Helmholtz coils in the lab. Now, this involves a lot of mathematics because there's a derivative, a first derivative, and a second derivative. But let me make sure we get the physics. That's actually, the physics is the easier part of this. And then the usefulness of it, I should mention too. But let me just read it here. It says you have 2 circular coils of radius r and of n turns. Okay, so I'm going to draw one coil for a moment and kind of draw it with n turns. Now they say that it has a radius of r. Okay. Now there are 2 of them, and so the second one is actually spaced a distance of r from the first one. And the reason this is a great design is because in the location midway between the 2 coils, we can show that the change of the field as you move along in an x direction is 0. So that means the slope is 0. In other words, you have a pretty stable field. It doesn't change. It's a uniform field. And that is what Helmholtz was trying to do. He was trying to come up with a design that if you ran current, he could get a uniform field. And more than that, the second derivative is 0. As you know from your math class, if the first derivative equals to 0, that just means you might peak up at a maximum or peak down at a minimum, but it could be changing. But if the second derivative is 0, that means it has no concavity to it. And so functions that look like this would, maybe do something like this. Maybe they would go up and they would have to plateau before they drop down. And so in this little area, he noticed that not only is the first derivative 0, but the second derivative. So not only do we have a constant field, but the field is not even changing. It's not curved. The concavity, the rate at which it changes is 0. And so that means that you have to go a pretty good distance away from the center point before the field gets weaker or stronger. It actually gets stronger. So as we get closer to these, I probably should have done something that dipped down like that as I draw the field and X. And so just to give you some engineering background, Helmholtz was the one who really came up with this plan and this design, and that's why we call them today Helmholtz coils. And he started using them as a way to make a uniform, and it's not perfectly uniform. If you take the third derivative, it's not 0, but it's pretty darn close. And so as long as you do everything right in this concentrated area, you could say that you have a uniform field. And that's why in the lab this week, when I make it, you see the video of it. Oh, wait, this week? No. I already made the video for this one coming out next week. But so next week, I have to make a video for the following week. So the week of the test, you'll probably focus on the test first. But if you have some extra time, you can do the lab. And I talk a lot, and you'll see our Helmholtz coil. If you've ever, unfortunately, needed to get an MRI, or I guess these days, MRI, magnetic resonant imaging, for the machine to work, you have to put the patient in a very strong uniform field. And so the patient lies right on a little bed right here, and to their left or right, or top and bottom, depending on how they want to build it, there's these huge coils. And I know when my son was in there doing the MRI, we put him on this little gurney, and they put him in there. And while the technician was running all the tests, I just kept fiddling and touching the big coils on the side. Finally, he had to ask me, "What are you doing?" I'm like, "Well, these are Helmholtz coils, right?" Anyways, and so we got into discussion a little bit about the magnetism and the way the MRIs work. Anyway, so but it's a like I said, it's a brilliant design. So I know that's not part of the question, but hopefully that will help you in your future about in terms of engineering and science and why these are so special and have their own name, the Helmholtz coils here. All right, so let me put an equation that was derived in the book and in the lecture using the B-ups of art. And without going back and re-deriving it, although I'll gladly do that if you want me to, there's enough to do in this problem. Let me start here. This is the equation that I would encourage you to have close at hand as you're doing the homework and the test. This is the magnetic field from a ring. So let me just kind of explain this equation. And so here is a ring. And if you take the axis of symmetry to be the x-axis, this equation tells us the magnitude of the magnetic field along the axis of symmetry, a distance x when the ring has a radius of a and a current of I is flowing in it. So there's the I, there's the A, there's the X. So I'm going to apply this equation to ring number 1. So let me say magnetic field number 1. And so coming back to the picture I drew before I got all involved with the math of Helmholtz coils and first and second derivatives, let me just say this is ring number 1. And so I would have the mu naught, and I would have the current that is in ring number 1. The equation was derived with a radius of a, but this problem says the radius is r squared. So I'm going to replace the a with an r squared. And the same thing in the denominator, I'm going to replace the a with an r squared. Now, the x is the distance along the axis of symmetry. And so what we're asked to do here in this problem is to find the magnetic field halfway between the coils. So in other words, x is r over 2. And of course,
I thought part one was just asking for x at any point.
Oh, you're right. Got ahead of myself. Sorry. Yep. Show that the magnetic field on the axis at a distance x. Okay. Yep. My bad. So I'll just leave that as x squared. Thank you. Okay. So some distance away. We're not in the center yet. Okay, but we're going to prove that. That's the magical spot. Okay, so that's the x. Now, also, let me throw in another factor because Helmholtz coil here has n turns in it, whereas this equation was derived for just a single current of loop. So I need to multiply by n to make it match the field from one of the set of coils. Okay, so that's why I'm going to throw in a factor of n. It's not in the original equation, but the original equation is hopefully me knowing that that was only for one loop. So I've got to multiply by however many loops I have, and they say there are n of them. Okay. Now, the second Helmholtz coils would be the kind of the same logic. It would be radius of A. The radius A, I'll just put in R. But this is the part where I need to be careful. If you have your two Helmholtz coils, and maybe on this page 2, I'll just say here is coil number 1, and here is coil number 2, and I'm trying to get the field, let's say here at some random point x, then this distance would be r minus x, because the whole distance between the two coils is r. And coming back to the meaning, and this is important, the meaning of this x is how far you're from the center of the coil. And so for coil number 2, I am a distance of r minus x. And so I need to be careful on the meaning of my x. I'll say it again. The meaning of my x is how far this point where I want to get the magnetic field is from number 1. That's why the x in this equation and the x here are the same. But for coil number 2, using this equation, x is how far you are away from the center of number 2. And so how far away am I from number 2, written in terms of x, would be r minus x. Okay, and so that is one of these causes you've heard me say, don't just do the math, read the math. What is the meaning behind this x? And the meaning behind this x is not the same as the x along this axis from coil number 1 to coil number 2 that I want it to be. So I got to replace this x with the x along this axis. Now, let me also point out that coil number 2 also has n number of turns, so I got to multiply that one by n. Now, for the total field, I would have to see how these two vectors add together, because as you know, if they're both making a field, if they are in the same direction, you just add them. So here's two vectors in the same direction, you add them. But if the vectors are in opposite direction, you have to subtract them. And if the vectors are at 90 degrees to each other, you got to use Pythagorean's theorem to figure out what the magnitude is. So I'm going to then say, how do I put the field from number 1 together with the field from number 2? Do I add them? Do I subtract them? Do I do them in Pythagorean's theorem or some other thing? So let's take a look back here. and see how this thing is built. If you look at this, they say the current in the first coil is going around, which I guess if I was looking at it from my right this way, this would look like a counterclockwise direction. And the second coil, they label the same way. So the currents are each going in a counterclockwise direction if I am looking at them from the right side of this picture. I guess if I was looking from the left side, it would be clockwise, but let me not confuse you. So if I'm looking at it from the right side of this picture, looking this way, this would be going in a counterclockwise direction. Well, let me take this as an opportunity to do right-hand rule number 2 again. Okay, so right-hand rule number 2, remember it's not the cross product one where I move the fingers. Number 2 is where I just make the thumbs up symbol. Okay, and this will give me the direction of the magnetic field, but I've got to decide, do I use my thumb for the current or do I use my fingers for the current? And you want to match whatever shape you have. So when I was showing you this earlier, the shape I had was a long straight wire, so I was using my thumb for the current, but now I have loops of wire. So I'm going to use my fingers for the current. And my thumb then is going to give me the field. So if I take my right hand, get up here and circle around, but if I hold my right hand right here, then this is looping around, my fingers are looping around what from this observer looks like a clockwise direction. So using my green marker here, I would say that this first coil is giving me a magnetic field pointing towards the observer. So that's the direction of magnetic field number 1. Let me do that same logic and say, okay, what is the direction of the magnetic field from coil number 2? Well, you can kind of see I'm just going to end up holding my right hand in the same fashion. So this right here would say that the magnetic field is also in the same direction. And of course, I just drew it in the center, but it would be true over here. Both of them would be pointing in that direction. It would also be true over here. Both of them would be pointing in that direction. It would be true kind of in the center of coil number 1. They would be both pointing in the same direction. And so this arrangement we see is a useful one for creating a magnetic field. It doesn't cancel off. They add together. And it kind of makes sense. They're both going in the same direction. All right. So coming back to my mathematics, I would then say the total field created in this situation is field 1 plus field 2. They add together. And they're going to be in the x direction. So not putting an I hat or anything, I will just add them together. So the first one would be an n, a mu naught, an I, an r squared over a 2, and then we have this r squared plus x squared to the 3/2 power. And the second one would then be the n, the mu naught, the I, the r squared, the 2, the r squared plus r minus x squared to the 3/2 power. In fact, you can begin to see then if it's right in the middle, these two are going to be the same number. So that's eventually where we're headed with this. That the field in the middle is equal amount from both of them and they add together. But if I factor out common factors, they each have an n, they each have a permeability of free space, they each have a current, they each have a radius squared, they each have a factor of 2. The part that, and say, what are we trying to get here? Yeah, it says show that it looks like this. And so I think I factored out the first part. Okay, good. Then I would be left with this first term, which is 1 over, and this would be an r squared plus an x squared to the 3/2. And so good, that's the first term. And the second term, they worked out a little bit. They did this binomial expansion because r minus x squared, you remember a minus b squared would be r squared minus 2ab plus b squared. So if you multiply out this binomial here, you would have 2r squareds. Then you would have also a plus an x squared from this one, and then minus a 2rx. And all of this, of course, is still raised to the 3/2 power, which they don't multiply out. But we get what they want us to get. And so here's the answer to A. Show that the magnetic field would be this. So it's a function of x. And so, again, we can now figure out what the field would be at any value between the Helmholtz coils. Again, not just the center, as I started to focus my attention on. So let me go back to the question A. So question A, the coil centers are a distance r apart. Each coil carries a current I in the same direction as shown. Show that the magnetic field along the axis, the distance x from the center of the first coil is given by this. Okay, so we did that. The stuff that's a little more mathematically intense here is show that, and then they say the first derivative and the second derivative are both 0. And okay, I'll do that, but I'm going to point back to what I got kind of lost in a conversation, that this is actually very useful, that you can show that the derivative is 0 at the midway point, meaning that at the midway point, you have not only this maximum field here, or minimum, but it's very stable. There's no concavity to it. It's not changing. And so there's a space where the field is 0. In fact, that'll give me a chance to say, use your calculus, read your calculus. Don't just do it. Don't just take a second derivative. But what does a second derivative mean? And second derivative is the concavity of it. How much is it changing? And so it's changing very little in that space. And so this is Helmholtz' clue to say, hey, this is a nice uniform field. All right, so now let me go ahead and take the derivative. If it'll be okay with you, let me just kind of put all of this stuff as one variable. Since it doesn't have an x in it, let me just call it, what would be a good variable? I'll just start at the beginning of the alphabet. We don't have any capital A's around, do we? So let's just call all this capital A. So if I do that, then maybe I'll move to another sheet of paper real quick. I now have the magnetic field is this capital A times, and maybe I'll bring this equation real close here. I have an r squared plus an x squared to the negative 3/2 power. And so I'm just going to bring it out of the denominator, mostly because I know I'm taking a derivative and I would much rather do product rules versus quotient rules. So I'm going to give it a negative exponent. And then the same thing here, plus, and this is 2r squared plus x squared minus 2rx to the negative 3/2 power. Okay, so that is the magnetic field. So if I take the first derivative, dB dx, of course, the A is a constant, so I'll leave that alone. And when I take the derivative of this guy, you bring down the exponents and then subtract 1 from the exponents, and then you do the chain rule. which the chain rule would say no derivative for the r squared, but derivative of x squared would be 2x. Okay. So then, if I also take the derivative of this piece, you bring down the exponents, and you take the same function and subtract 1. Then you do the chain rule, and I might be out of space, so I'm going to put it down here. Nothing from that, but this would be a 2x. And then this would be minus a 2r. And so there's a little time symbol there between those two. Okay. Now, I have this a. Maybe I'll even notice, just for the sake of simplifying things, there is a 2 here, which would cancel with that 1/2. And you would also see it in the other term, where this 2 can be factored out and cancel with that one. Okay, that's kind of nice. And then also this, when I took this derivative, this -3 is in each term, so I can factor it out. So if I've done that right, I have an x still left in the numerator. And if I bring this down, this becomes an r squared plus an x squared to the 5/2 power. So there's the -3, took care of the 2, there's the x. And this one here, the numerator would be the x minus the r. And then downstairs would be this 2r squared plus x squared minus 2rx to the 5/2 power. Okay. Now, continuing on, maybe I'll put the -3 before the a. That's kind of tradition. So I'll put the number and then the symbol. Okay, so there's the 3a. But most of the time, solving a problem like this, you need to get a common denominator. I don't see a lower common denominator than just multiplying them together, but there might be. So this would be a common denominator, but maybe not the lowest. But I think that's the lowest common denominator. Okay, so what that meant is the first term, I had to multiply the bottom by a 2r squared plus x squared minus 2rx to the 5/2 power in order to get that to be the same common denominator. It also means that over here, I would have an x minus an r Okay. Yeah, I don't see a shorter way to do this. There might be, though, but I'd have to multiply this by an r squared plus an x squared to the 5/2 power. Okay, now, if we're trying to show where this equals to 0, notice that if I set this equal to 0, the only place it can equal 0 is if this numerator is 0. Or put another way, if I divide this side by negative 3a, that goes away and you still have a 0. If I multiply it by this term and move it over to there, it's still a 0. And if I move that over to there, it's still a 0. So for this to equal to 0, this statement must equal 0. So that kind of simplifies a lot. I get rid of the denominator and the a and the negative 3. I don't have to worry about those. Okay. Now, why don't I do, yeah. Looking for an easier way. I'm just thinking there must be an easier way. Maybe I should have found a different common denominator. Actually, I don't think the author wanted me to find the value of x. They want me to show that if I set x equaling to r over 2, I would get 0. So I think I started to go down the wrong road. I was solving it to prove that it would equal 0 at r over 2. And maybe that's why he worded it this way, because he sees that, look, you have to move things to both sides, then you have to square it, then you have to take a fifth root. So you could prove it, but it's easier to show. So my apologies. Let me go back to this step here and show that it equals 0, because if I just write this as 3a, and I put in x equaling r over 2, I would get down here, this x squared would become an r squared over 4. So when I add it to the 1, let me just write it this way, r squared over 4 for now. Okay, plus. All right. So here in this numerator, if I put x as r over 2 and I subtract an r, that's a minus an r over 2. And over here, I would have something that looks like 2r squared, and then this would be plus an r squared over 4, but then this would be minus just an r squared, because the x would be an r over 2. The 2 would cancel. But this is why I'm pretty sure he used the words show. Because if you look at this denominator and compare it to that denominator, you will see that this 2r squared, when you subtract off a 1r squared, leaves you with 1r squared plus an r squared over 4 raised to the 5/2. So when x is equal to r over 2, these denominators are the same. And so they already have a common denominator. You don't have to go through the math I was about to go through. And then you would have then in the numerators would be equal and opposite. So obviously when you have two fractions that have the same denominator, but the numerators are equal and opposite, you just, add across the numerators and you get 0. All right, so that's how you show, not prove, but you show that it is equal to 0. All right, so definitely the first derivative is equal to 0, which of course mathematically tells us that the magnetic field between them is either a minimum or a maximum. Now, to also show it's not a reflection point, or it doesn't have any concavity, we need to do the second derivative. And again, not prove, but show that that one is also equal to 0. So let me come back to this, which was the first derivative. And so let me just rewrite it. So let me scratch out the second derivative there. All right, so I've got my negative 3a for my first term, and I'm going to write this as x times r squared plus x squared to the negative 5 over 2. So that'll be kind of my easy way, if you will, taking the derivative, because I don't want to do a quotient rule. And then this one here would be 2r squared plus x squared minus 2rx to the negative 5/2. All right, so let me give myself a little bit of room. I don't even know if I can fit this on one line, but let me now take the second derivative. So I'm still going to have the negative 3a. But I need to do a product rule here. So it would be the first times the derivative of the second. And the second would be, again, bringing down the exponent and subtracting 1 from it, and then doing the chain rule. So that's the first times the derivative of the second. And then the second, so r squared plus x squared to the negative 5, times the derivative of the first. Well, that's just a 1. All right, so there's my product rule. Here's where I'm going to need a whole nother row here. So now I got to take the derivative of that term, which again is a product rule. So it's the first times the derivative of the second. So minus 5 over 2. And then it would be this 2r squared plus x squared minus 2 rx to the negative 7 over 2. Then, of course, then the chain rule for this would be a 2x here minus a 2r. Okay, so that's the first times the derivative of the second, plus the second, so this would be 2r squared plus x squared minus 2rx, times the derivative of the first, which would just be a 1 in closing. All right, so there are my 4 crazy terms that I have. And I'll say it again, they're not asking us to prove that it equals 0. They're saying if you put in x equaling r over 2, you will get a 0. Let me hold off on putting in the x value yet, just so I can simplify it. But I'll simplify this first one kind of like we did before. It looks like here that this 2 would cancel with that 2, and I would have a negative 5 and an x squared left here, and then if I move the r squared plus the x squared down to the denominator, I would have it to a 7/2 power. I would then just have a 1 over a r squared plus an x squared to the 5/2 power, that term. This term I'll put down on a new line. But like we did before, I could factor out a 2, which would cancel with that one. So we would have a -5 here. And then I would have an x minus an r. So there's the -5. I have an x minus an r. I think that's everything that I want to leave in the numerator. And let me put my 2 r squared plus my x squared minus my 2 r x into the 7/2 power. I hope I didn't make a mistake here, a lot of math. And then this last term, I'll just leave the 1 upstairs. And I think I forgot to put the -5/2 there, right? Because it would be the second times the derivative of the first. Yeah, so this should go downstairs as a 2 r squared plus an x squared minus a 2 rx to the +5/2 when it's downstairs. All right, well, believe it or not, we're almost done. The math here. Because if you kind of remember when we did the first derivative, when we plugged in the value x equals to r over 2, and so I'm going to come back to where we did the first derivative back here, and point out that this one right here, which was r squared plus x squared, when we put in an x equaling r over 2, we got for both cases r squared plus r squared over 4. And so they became like terms in the denominator, okay? Now we're going to have a little troubles with this one because we've got 4 terms, but what I'm going to do is take advantage of that and do this. That the numerator here is going to be a -5, and I will put an r squared over 4 for that x. But down here, I know that every time I put that x in there, this is going to be an r squared plus an r squared over 4, and that would be to the 7/2 power. Now I say that because down here I have this 1, and I'm going to have then an r squared plus an r squared over 4, but this time it's to a 5/2 power. So these are not common denominators, but at least the part that's not raised to a power here, the base of it, and this is the exponent, so the base of the exponent is the same. And then likewise here, I have a plus, and I'll put the -5. But remember now, if I put x equaling to r over 2, this becomes minus r over 2. And then downstairs for this one, this would still be the r squared plus the r squared over 4 raised to the 7/2 power. And then this one here would be the 1 plus, and then this would be the r squared plus the r squared over 4 to the 5/2 power. Okay, so I would say that not quite, but I almost have a common denominator here. I'll still leave my 3a over here. But now I'm going to make a common denominator that is r squared plus r squared over 4 to the 7/2 power. You see, the first and the third term are to the 7/2 power. So all I would need to do is to multiply this bottom by r squared plus r squared over 4. Of course, I'd have to do it on the top, r squared plus r squared over 4. And then I would have a 7/2 power down here. And likewise for this term. In fact, I didn't notice this till just now. The second and the fourth are identical. Did I make a sign error? I would have thought those were going to come out to be the opposites, but maybe not. All right, I'm going to keep going. I don't think I did a sign error. But here's what I'm trying to say then, is I can take all 4 of these terms, and in fact, the second and the fourth I can combine, and I can get a common denominator of r squared plus r squared over 4. And this one here is already like that. So it's a minus 5 r squared over 4. The third term is then a plus because the negative and negative is a plus, okay. And this would be a 5r over 2. And this last term, if these two are the same, I'll put a 2, and then this would be times an r squared plus an r squared over 4. All right, now if all this is going to come out to be 0, that means this part right here has to come out to be 0. So this first one is a minus 5/4 r squared. And that didn't quite work, did it? Because that's a 2.5 and that's a 2, so that's much bigger.
It makes sense if like there was probably a sign error in the previous step because there were only 2 terms, really. One of in the previous step, just one of them was negative and one of them was positive, but then that wasn't the case with the 1 over r squared plus r squared over 4 to the 5/2.
Yeah, yeah. So that one here, first times the derivative of the second, then the second times the derivative of the first. Then down here, here's the first times the derivative of the second. Well, I don't quite see it, but you know what? I'm going to do something here. This right here in decimals would be a negative 1.25 r squared. This in decimal would be 2.5. Oh, now I only have an r and not an r squared. And that makes me think I also did something wrong. the derivative. Because I can't get it to equal to 0 unless I have all the same powers. So that's this third one here. Oh, there it is right here. I totally missed that right there, squared. Because there was that one and that one. And so that should have been an x minus an r squared. So that's this third term. So it would have squared that one, which would have made that an r squared over 4 and left it as a negative. Let's see if that fixes it. And so these are identical. And so I'll put a minus 1.25 r squared. So that's 2.5. And then this would be 2.5. Yeah, this would be 2r squared plus a half r squared. Yeah, okay, good. So that's 0. So yeah. So I missed that term and that term. I just in my mind saw them as one term and didn't square it. Good. And so that's the, I told you when I started this, I thought, oh, this looks like a lot of math. And to be quite honest, I'm not even sure how valuable the math is as much as the physics part of it, as these are two Helmholtz coils that you're going to add together. So I hope you saw that. I used the right-hand rule to get the direction. I used the equation for a coil. That's the big thing. But the result is kind of nice too. That's why I actually picked this problem, even though it was kind of mathy in the derivatives. It's such an important one, and we do it in the lab. It's nice to know why Helmholtz coils are such a powerful and useful tool. And so now I'm even more happy that he said show it equals to 0, not prove it equals to 0, because setting that equal to 0 and solving would have been a lot more. It was already a lot. Yeah. All right. Well,
Thank you, by the way. Appreciate it.
Yeah, you're welcome. Looks like we're kind of way over time here, but I guess we'll call it quits for now. Do you have anything you want me to work out? We'll work it out on video, or questions I can type out, or other than that, I guess I'll see you next Friday.
All right, have a good weekend. See ya.
All right. Take care.
I actually have a quick question.
Oh, go ahead, Zach.
So this is less of a actual homework question, more of just maybe if in the coming week maybe they could another session of this on a different day. Do you think you could do like one of these on like Wednesday?
Oh, do an extra one to get ready for the test?
Yeah.
Yeah, maybe. Okay, yeah, we should work something out here. Let me look at my schedule and let you guys know. Yeah.
Yeah, because for me, I mean, I tend to work most Fridays like 8 to 1, so I miss 2 of the whole things that you have for this, and that makes it a little bit, even if you do end up posting the videos later.
Okay. Now let me ask you though. Now the video ones I sent out where we're not live face to face. Are those helpful for you?
They're still helpful, but every once in a while, like as I'm watching, it's like, oh, I wish I could ask a question here or there, and then I end up doing other things and figure it out.
Oh, so let's do both. Let's see if we can squeeze another one with a big test coming in here for review, and then also, but the other big thing is if you're struggling with one. Especially if you did this would be actually really good. Let's say you're watching, like number 14 I said is a good one to watch because I spent a lot of extra time trying to focus on those angles. And so you might have a specific question in there. So feel free to answer that question and timestamp it, and I can be very specific. And if it's more general that I think will help everybody, I'll make a small little video of that and say, hey, here's a supplement to that one. That's what I start to do when things get real complicated. We have the supplement. It's kind of like a debate where you have a debate and a rebuttal to the rebuttal. And so it's helpful to have a rebuttal to the rebuttal, not just here's my argument and then nothing goes from there. But it's nice to rebuttal it, and so you can kind of zoom in on a solution that way.
Yeah.
So, and it also gives me a chance to draw pictures and stuff. Especially specifically knowing that okay, how did you hold your right hand? Because that's usually a lot of the question. How are you holding your right hand? And so I can do a screen capture of somebody with their right hand instead of trying to do it to the camera. And I almost think that one works better than me trying to show you my right hand to the camera.
Okay. Yeah, because I was looking at your whole discussion of number 18 from chapter
Yeah.
30. And I know that was only kind of like part of it because you'd already done some in the previous section, which I was happy part of. So I'll be reviewing that and what we did in this one to make sure I have all the context.
Right.
And I know that you kind of went into a bunch of stuff. It's like, well, I know the question isn't really asking this, but this is all a bunch of useful information. So
Right. And that's why I said I'm glad you're working on it because this really takes 2 weeks. So we're 1 week into it or almost a week into it. I'll call Sunday a week into it. So keep working on those because it really takes the second week to get this straight.
yeah. All right. Thank you very much. Appreciate that. And
All right.
yeah, have a nice weekend.
All right. You too.